All right, welcome back. It's been minutes. Next on deck, residual entropy. Turns out you can actually break the third law. You may or may not recall that the third law was the statement that the entropy of a perfect crystal is 0 at 0 Kelvin. So actually that turns out to be true. The question is, do you always get a perfect crystal, and what happens when you don't? So here's kind of the classic example of this. Imagine you are depositing carbon monoxide onto a surface that is well below its freezing point, so it's going to condense. Now, carbon monoxide is polar, so the oxygen has a partial negative charge, the carbon's going to have a partial positive charge. So you would think, if you're doing a nice simple two-dimensional array here, that you would make sure that the carbon of one molecule is aligned with the oxygen of an adjoining molecule and vice versa. So you'd expect this rough ordering. Well, you alternate between a carbon-oxygen, carbon-oxygen. But that means that there's a preferred orientation for these carbon monoxides molecules when they solidify. Now there's some other things. Now the polarity is not that great, and it turns out that carbon and oxygen have very similar size. So it would be very simple for one of these to actually kind of fall in the wrong way. And then kind of get trapped there once the next wave of molecules comes in here. Well, so that means that there is some uncertainty in the orientation of this. So this isn't a perfect crystal anymore. So what would be the entropy of this? Well, remember, Boltzmann distilled entropy into this expression right here. It's equal to k times the natural log of the ways to arrange your thing. So in this particular scenario, the carbon monoxides would actually have more, could adopt one of two possible orientations. And that would imply that for an n molecule chunk of solid carbon monoxide, there are 2 to the n possible ways of laying these out. So the entropy of this imperfect carbon monoxide crystal at 0 Kelvin would be equal to, and let's say that we did a mole of carbon monoxide atoms in this, or molecules I should say. So that is going to be Avogadro's number times k times the natural log of 2. Which is equal to r times the natural log of 2 if you want to do that. And this ends up being 5.8 joules per mole per Kelvin. And so this is referred to as the residual entropy. And this is a thing when something can crystallize, if it might actually, if it can possibly take a couple of different orientations. So generally, for x orientations, you go with n times r times natural log of that number of orientations x, or number of particles times k, natural log of x. So for example, let's say so benzene crystallizes, it has maybe 6 possible orientations, but they're all the same. But just keep in mind, what about So, what if one of the hydrogens was now a deuterium? And this might not have residual entropy, and this one might. All right, and that's residual entropy. See you in a little bit.